Multithreading and concurrency interview questions. 26 questions. Difference between parallelism and concurrency? Concurrency is when two tasks can start, run, and complete in overlapping time periods. Parallelism is when tasks literally run at the same time, e.g., on a multi-core processor. Concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once. One word. Concurrency, interruptibility. Parallelism, independentability. Example, let's say you have to get done two very important tasks. Passport task. Prepare for presentation. Concurrency. While you are waiting in passport queue and worked on presentation, this situation is called concurrency. In this case, both tasks are done by you, just in pieces. You interrupted the passport task while waiting in the line and worked on presentation. When your number was called, you interrupted presentation task and switched to passport task. The saving in time was essentially possible due to interruptibility of both the tasks. Parallelism. You have got an assistant. So, before you leave to start the passport task, you call him and tell him to prepare the first draft of the presentation. You spend your entire day and finish passport task and will get presentation. Now, since your assistant is just as smart as you, he was able to work on it independently, without needing to constantly ask you for clarifications. Thus, due to the independentability of the tasks, they were performed at the same time by two different executioners. 2. Race condition in Java. When more than one thread try to modify a shared resource at the same time. Multiple threads executing inside a method is not a problem in itself. Problem arises when these threads try to access the same resource. Examples of shared resources are class variables, DB record in a table, writing in a file. 3. Why wait, notify and notifyAll in inside object class. These methods works on the locks, and locks are associated with object and not threads. Hence, it is in object class. The methods wait, notify and notifyAll are not only just methods, these are synchronization utility and used in communication mechanism among threads in Java. 4. Why notify and notifyAll method call inside synchronized. We can call wait, notify and notifyAll methods within the synchronized when the thread has the object's lock. If notify method is not within synchronized block, then it would be useless to place wait into synchronized block. Take scenario of producer-consumer model. Producer and consumer, both the methods will execute concurrently because one of them is not synchronized. There will be a race condition. Calling methods from outside the synchronized method or block. If you call wait, notify and notifyAll methods within a method that's not synchronized, the program will compile, but when you run it you'll get an illegal monitor state exception. 5. Happens before relationship in multithreading? See an example. Let's assume that the above two snippets being executed by two different threads, thread 1 and 2. When the first thread changes has value, it will not only flush this change to main memory, but it will also cause the previous 3 writes, and any other previous writes, to be flushed into the main memory as well. As a result, when the second thread accesses these 3 variables, it will see all the writes made by thread 1, even if they were all cached before, and these cached copies will be updated as well. Similarly, the JVM will also not change the order of a statement which appears after a volatile variable read to appear before the access. Which means the following dash. See an example. However, the JVM can certainly reorder the last 3 reads among them, as long as they keep appearing after the volatile read. 6. Difference between volatile, atomic and synchronization. Declaring a variable as volatile means that modifying its value immediately affects the actual memory storage for the variable. The compiler cannot optimize away any references made to the variable. This guarantees that when one thread modifies the variable, all other threads see the new value immediately. This is not guaranteed for non-volatile variables. Declaring an atomic variable guarantees that operations made on the variable occur in an atomic fashion, i.e., that all of the substeps of the operation are completed within the thread they are executed and are not interrupted by other threads. For example, an increment and test operation requires the variable to be incremented and then compared to another value. An atomic operation guarantees that both of these steps will be completed as if they were a single indivisible, uninterruptible operation. Synchronizing all accesses to a variable allows only a single thread at a time to access the variable, and forces all other threads to wait for that accessing thread to release its access to the variable. Synchronized access is similar to atomic access, but the atomic operations are generally implemented at a lower level of programming. Also, it is entirely possible to synchronize only some accesses to a variable and allow other accesses to be unsynchronized, e.g. synchronize all writes to a variable but none of the reads from it. Synchronized versus atomic versus volatile. Volatile and atomic is apply only on variable, while synchronized apply on method. Volatile ensure about visibility not atomicity, consistency of object, while other both ensure about visibility and atomicity. Volatile variables store in RAM and it's faster in access, but we can't achieve thread safety or synchronization without synchronized keyword. Synchronized implemented as synchronized block or synchronized method while both not. We can thread safe multiple lines of code with the help of synchronized keyword, while with both we can't achieve the same. Synchronized can lock the same class object or different class object while both can't. 7. Deadlock condition in multithreading. When two or more threads waiting for each other to release lock, that situation is called deadlock. See an example. Deadlock preventions. Avoid nested locks. This is the main reason for deadlock. Deadlock mainly happens when we give locks to multiple threads. Avoid giving lock to multiple threads if we already have given to one. Avoid unnecessary locks. We should have lock only those members which are required. Having lock on unnecessarily can lead to deadlock. Using thread join. Deadlock condition appears when one thread is waiting for the other to finish. If this condition occurs, we can use thread join with maximum time you think the execution will take. Detect deadlock. If possible, first we need to check our code for nested lock and unnecessary lock. Another way to determine deadlock risks is when you actually get deadlocked while running the application. If this happens, try to take a thread dump. In Linux you can do this by the command kill -3. This will print the status of all threads in an application log file, and you can see which thread is locked on which object. 8. What is compare and swap cas or compare and set cat? In multi-threaded Java programming, when a shared resource is accessed by multiple threads concurrently, shared data needs to be synchronized for access and visibility. But synchronization enforce locking and block all the threads but one trying to access the resource. This is optimistic approach of enforcing single access to shared resource at one time, but it results huge degradation in multi-threaded environment. So there is one optimistic approach, that is CAS, compare and swap. What happens here is that a thread approach a shared resource with three variables. A. Current expected value. B. New value. C. Memory address of the resource. So thread will access data from memory address, will compare the current value with current expected value. If they match, it will update the variable to new value. Obviously, if multiple threads try making this operation simultaneously, only one thread will succeed and others will fail. but other threads will not block. Instead, invoker can continue with other operation or try the same again with failing threads. So this provides a lot better performance. Compare and set. Compare and set is same as compare and swap. Only difference is that it returns a Boolean value as well as which determines if operation succeeded or not. Atomic variables. Atomic integer internally uses compare and set method non-blocking algorithm. See an example. (9) Producer-consumer problem in multithreading. Problem statement. There are two processes, a producer and a consumer, that share a common buffer with a limited size. The producer produces data and stores it in the buffer, and the consumer consumes the data, removing it from the buffer. Having two processes that run in parallel, we need to make sure that the producer will not put new data in the buffer when the buffer is full, and the consumer won't try to remove data from the buffer if the buffer is empty. Solution. For solving this concurrency problem, the producer and the consumer will have to communicate with each other. If the buffer is full, the producer will go to sleep and will wait to be notified. After the consumer will remove some data from the buffer, it will notify the producer, and then, the producer will start refilling the buffer again. The same process will happen if the buffer is empty, but in this case, the consumer will wait to be notified by the producer. If this communication is not done properly, it can lead to a deadlock where both processes will wait for each other. Approaches. Lock and condition. Wait and notify. BlockingQueue. Thread pool executor framework. 10. Object-level lock versus class-level lock. Object-level lock is mechanism when we want to synchronize a non-static method or non-static code block such that only one thread will be able to execute the code block on given instance of the class. This should always be done to make instance-level data thread safe. Object-level locking can be done as below. Various ways for object-level locking. See an example. Class-level lock prevents multiple threads to enter in synchronized block in any of all available instances of the class on runtime. This means if in runtime there are 100 instances of demo class, then only one thread will be able to execute demo method in any one of instance at a time, and all other instances will be locked for other threads. Class-level locking should always be done to make static data thread safe. As we know that static keyword associate data of methods to class level, so use locking at static fields or methods to make it on class level. Various ways for class level locking. See an example. Lock I. Whenever a thread enters into Java's synchronized method or block, it acquires a lock, and whenever it leaves synchronized method or block, it releases the lock. Lock is released even if thread leaves synchronized method after completion or due to any error or exception. Java synchronized keyword is reentrant in nature. It means if a synchronized method calls another synchronized method which requires same lock, then current thread which is holding lock can enter into that method without acquiring lock. Java synchronization will throw null pointer exception if object used in synchronized block is null. For example, in the above code sample, if lock is initialized as null, the synchronized lock will throw null pointer exception. It's possible that both static synchronized and non-static synchronized method can run simultaneously or concurrently because they lock on different object. Do not synchronize on non-final field on synchronized block in Java, because reference of non-final field may change anytime and then different thread might synchronizing on different objects, i.e. no synchronization at all. Do not use string literals because they might be referenced elsewhere in the application and can cause deadlock. String objects created with new keyword can be used safely. But as a best practice, create a new private scoped object instance or lock on the shared variable itself which we want to protect. Lock 2. 11. Lock interface in Java. Lock is a more flexible and sophisticated thread synchronization mechanism than the standard synchronized block. Lock and synchronized block. A synchronized block is fully contained within a method. We can have lock API's lock and unlock operation in separate methods. A synchronized block doesn't support the fairness. Any thread can acquire the lock once released. No preference can be specified. We can achieve fairness within the lock APIs by specifying the fairness property. It makes sure that longest waiting thread is given access to the lock. A thread gets blocked if it can't get an access to the synchronized block. The lock API provides try-lock method. The thread acquires lock only if it's available and not held by any other thread. This reduces blocking time of thread waiting for the lock. A thread which is in waiting state to acquire the access to synchronized block can't be interrupted. The lock API provides a method lock interruptably which can be used to interrupt the thread when it's waiting for the lock. A locked instance should always be unlocked to avoid deadlock condition. A recommended code block to use the lock should contain a try, catch and finally block. See an example. In addition to the lock interface, we have a read-write-lock interface which maintains a pair of locks, one for read-only operations, and one for the write operation. The read lock may be simultaneously held by multiple threads as long as there is no write. ReadWriteLock declares methods to acquire read or write locks. LockReadLock returns the lock that's used for reading. LockWriteLock returns the lock that's used for writing. 12. What is ReentrantLock? ReentrantLock class implements the lock interface. It offers the same concurrency and memory semantics as the implicit monitor lock accessed using synchronized methods and statements, with extended capabilities. Let's see how we can use ReentrantLock for synchronization. See an example. We need to make sure that we are wrapping the lock and the unlock calls in the try-finally block to avoid the deadlock situations. See an example. In this case, the thread calling try-lock will wait for 1 second and will give up waiting if the lock isn't available. 13. What is ReentrantReadWriteLock? ReentrantReadWriteLock class implements the ReadWriteLock interface. Let's see rules for acquiring the read lock or write lock by a thread. Read lock: if no thread acquired the write lock or requested for it, then multiple threads can acquire the read lock. Write lock: if no threads are reading or writing, then only one thread can acquire the write lock. Let's see how to make use of the read-write lock. See an example. For both the write methods, we need to surround the critical section with the write lock. Only one thread can get access to it. See an example. For both read methods, we need to surround the critical section with the read lock. Multiple threads can get access to this section if no write operation is in progress. 14. What is stamped lock? Stamped lock is introduced in Java 8. It also supports both read and write locks. However, lock acquisition methods returns a stamp that is used to release a lock or to check if the lock is still valid. See an example. Another feature provided by stamped lock is optimistic locking. Most of the time read operations doesn't need to wait for write operation completion, and as a result of this, the full-fledged read lock isn't required. Instead, we can upgrade to read lock. See an example. 15. Semaphore and mutex in Java. We can use semaphores to limit the number of concurrent threads accessing a specific resource. A semaphore controls access to a shared resource through the use of a counter. If the counter is greater than 0, then access is allowed. If it is 0, then access is denied. Methods. Try acquire-return true if a permit is available immediately and acquire it, otherwise return false, but acquire requires a permit and blocking until one is available. Release a permit. Available permits-return number of current permits available. Mutex or binary search. Mutex acts similarly to a binary semaphore. Only one thread to access a resource at once. See an example. Countdown latch. 16. Countdown latch versus cyclic barrier versus phaser. Countdown latch. Cyclic barrier. Phaser. When we start up our debit processing system, we can initialize and set up each of the three services in a serial fashion, one after the other. This can delay the startup time. The other approach is to initialize and set up the services in parallel threads. For this we need to ensure we do not begin processing any debit transactions until all the three services are initialized and set up. This is a one-time synchronization that needs to happen at startup. This is where the countdown latch synchronization mechanism comes in handy. A countdown latch allows one thread to wait for the other threads to complete some actions. A countdown latch is initialized with an integer count which represents the number of threads to wait for. The thread that needs to wait will invoke the await method. Each of the threads performing some actions will invoke the countdown method to signal the completion of some actions. Each instance of countdown latch object is good for one-time use. Now that our debit processing system is up and running, we will start processing debit transactions. Each debit transaction involves 3 steps: authentication, balance verification, and fraud verification. We can process these steps in a serial fashion, one after the other. This will reduce the processing throughput. The other approach is to process the 3 steps in parallel threads. For this we need to ensure that the main processing thread waits for the 3 steps to complete. Debit transaction processing is not a one-time synchronization operation. This is where the cyclic barrier synchronization mechanism comes in handy. A cyclic barrier allows one or more threads to wait for the other threads in the set to arrive at a common synchronization point called the barrier point. A cyclic barrier is initialized with an integer count which represents the fixed number of threads in the set. Each of the threads will invoke the await method which will block and wait for the other threads in the set to arrive at the barrier point. Each instance of cyclic barrier object is cyclic as they can be reused again once all the threads in the set have crossed the barrier point. A phaser is similar to a cyclic barrier except that it is more flexible and dynamic in terms of usage. With either the countdown latch or the cyclic barrier, one needs to specify the count of threads involved in the synchronization. With the phaser, the number of threads can be dynamic and vary with time. A phaser allows one or more threads to wait for the other threads in the set to arrive at a common synchronization point called a phase. To participate in the synchronization, a thread, also referred to as a party, has to invoke the register method on an instance of phaser. A thread will invoke the arrive and await advance method to block and wait for the other threads, or parties, in the set to arrive at the barrier point. A thread will invoke the arrive and deregister method to signal that it has arrived at the barrier point, without waiting for others, and also deregister from an instance of the phaser. Like the cyclic barrier, an instance of the phaser object can be reused again once all the threads in the set have crossed the barrier point. Invoking the method getPhase returns the current phase. Invoking the method getRegisteredParties returns the current count of threads, or parties, registered with the phaser. The following is the example that demonstrates the use of the synchronization mechanism countdown latch. See an example. The following is the example that demonstrates the use of the synchronization mechanism cyclic barrier. See an example. The following is the example that demonstrates the use of the synchronization mechanism phaser. See an example. Phaser. Phaser I. (17) Real-life example for mutex, semaphore, countdown latch uncyclic barrier. In a hypothetical theater, it is called mutex if only one person is allowed to watch the play. It is called semaphore if n number of people are allowed to watch the play. If anybody leaves the theater during the play, then another person can be allowed to watch the play. It is called countdown latch if no one is allowed to enter until every person vacates the theater. Here each person has free will to leave the theater. It is called cyclic barrier if the play will not start until every person enters the theater. Here a showman cannot start the show until all the persons enter and grab the seat. Once the play is finished, the same barrier will be applied for the next show. Here, a person is a thread, a play is a resource. BlockingQueue implementation in Java. A blocking queue is used where one thread produces objects and another thread consuming it. It solves the problem of producer-consumer because we don't need to handle waiting condition for both when producer wait for space and consumer wait for available object in queue. A blocking queue with one thread putting into it, and another thread taking from it. Java blocking queue implementations are thread-safe. All queuing methods are atomic in nature. It is not possible to insert null into a blocking queue. If you try to insert null, the blocking queue will throw a null pointer exception. It is also possible to access all the elements inside a blocking queue, and not just the elements at the start and end. For instance, say you have queued an object for processing, but your application decides to cancel it. You can then call g remove O to remove a specific object in the queue. However, this is not done very efficiently, so you should not use these collection methods unless you really have to. Java provides several blocking queue implementations such as array blocking queue, linked blocking queue, priority blocking queue, synchronous queue, and delay queue. First, the blocking queue example class, which starts a producer and a consumer in separate threads. The producer inserts strings into a shared blocking queue, and the consumer takes them out. See an example. Here is the producer class. Notice how it sleeps a second between each put call. This will cause the consumer to block while waiting for objects in the queue. See an example. Here is the consumer class. It just takes out the objects from the queue and prints them to system out. See an example. 19. What is callable interface? The Java callable interface, Java util concurrent callable, represents an asynchronous task which can be executed by a separate thread. For instance, it is possible to submit a callable object to a Java Executor service which will then execute it asynchronously. Callable definition. The Java callable interface is quite simple. It contains a single method named call. Here is how the callable interface looks, approximately. See an example. The call method is called in order to execute the asynchronous task. The call method can return a result. If the task is executed asynchronously, the result is typically propagated back to the creator of the task via a Java feature. This is the case when a callable is submitted to an executor service for concurrent execution. The call method can also throw an exception in case the task fails during execution. Implementing callable. See an example. This implementation is very simple. It has the generic type set to a Java string. The result of that is that the call method will return a string. The call implementation just returns a string representation of the current time in milliseconds. In a real application, the task would probably be a more complex, or larger, set of operations. Quite often, I/O operations like reading from or writing to disk or network are good candidates for tasks that can be executed concurrently. I/O operations often have long waiting times in between reading and writing blocks of data. By executing such tasks in a separate thread, you avoid blocking your main application thread unnecessarily. 20. Future interface. A Java future, Java. Util. Concurrent. Future represents the result of an asynchronous computation. When the asynchronous task is created, a Java future object is returned. This future object functions as a handle to the result of the asynchronous task. Once the asynchronous task completes, the result can be accessed via the future object returned when the task was started. Some of Java's built-in concurrency utilities, like e.g. the Java Executor service, return a Java future object from some of their methods. In the case of the Executor service, it returns a future when you submit a callable for it to execute concurrently, asynchronously. Java Future Interface Definition. To understand how the Java Future Interface works, here is an approximation of the interface definition. See an example. Each of these methods will be covered in later sections, but as you can see, the Java Future Interface is not that advanced. Get result from future. As mentioned earlier, a Java future represents the result of an asynchronous task. To obtain the result, you call one of the two get methods on the future. The get methods both return an object, but the return type can also be a generic return type, meaning an object of a specific class, and not just an object. Here is an example of obtaining the result from a Java future via its get method. See an example. If you call the get method before the asynchronous task has completed, the get method will block until the result is ready. There is a version of the get method which can time out after an amount of time has passed, which you can specify via method parameters. Here is an example of calling that get version. See an example. The example above waits for a maximum of 1000 milliseconds for the result to be available in the future. If no result is available within 1000 milliseconds, a timeout exception is thrown. Future I. Check if task is done. You can check if the asynchronous task is done, and a result available, by calling the future is done method. Here is an example of calling the Java future is done method. See an example. Check if task is cancelled. It is also possible to check if the asynchronous task represented by a Java future is cancelled. You check that by calling the future is cancelled method. Here is an example of checking if a task was cancelled. See an example. Cancel task. You can cancel a task, runnable or callable, submitted to a Java Executor service by calling the cancel method on the future return when the task is submitted. Cancelling the task is only possible if the task has not yet started executing. Here is an example of cancelling a task by calling the future. Cancel method. Future. Cancel. Future 2. 21. Difference between runnable and callable. The runnable interface is very similar to the callable interface. Both interfaces represents a task that can be executed concurrently by a thread or an executor service. Both interfaces only has a single method. There is one small difference between the callable and runnable interface though. The difference between the runnable and callable interface is more easily visible when you see the interface declarations. Here is first the runnable interface declaration. See an example. The main difference between the runnable run method and the callable call method is that the call method can return an object from the method call. Another difference between call and run is that call can throw an exception, whereas run cannot, except for unchecked exceptions, Subclasses of runtime exception. If you need to submit a task to a Java executor service and you need a result from the task, then you need to make your task implement the callable interface. Otherwise, your task can just implement the runnable interface. 22. Executor services. Once the thread has delegated the task to the executor service, the thread continues its own execution independent of the execution of that task. The executor service then executes the task concurrently, independently of the thread that submitted the task. Java Executor Service example. Before we get too deep into the executor service, let us look at a simple example. Here is a simple Java Executor Service example. See an example. First, an executor service is created using the executor's new fixed thread pool factory method. This creates a thread pool with 10 threads executing tasks. Second, an anonymous implementation of the runnable interface is passed to the execute method. This causes the runnable to be executed by one of the threads in the executor service. Executor Service I. 23. Implementations of Java Executor Service. The Java Executor Service is very similar to a thread pool. In fact, the implementation of the Executor Service interface present in the Java util concurrent package is a thread pool implementation. If you want to understand how the Executor Service interface can be implemented internally, read the above tutorial. Since Executor Service is an interface, you need to its implementations in order to make any use of it. The Executor Service has the following implementation in the Java util concurrent package: thread pool executor, scheduled thread pool executor. Creating an executor service. How you create an executor service depends on the implementation you use. However, you can use the executor's factory class to create executor service instances too. Here are a few examples of creating an executor service. See an example. Executor Service 2. 24. Usage of executor service. There are a few different ways to delegate tasks for execution to an executor service. Execute runnable, submit runnable, submit callable, invoke any, invoke call, shutdown, shutdown now, await termination, execute runnable. The Java Executor Service execute runnable method takes a Java lang runnable object and executes it asynchronously. Here is an example of executing a runnable with an executor service. See an example. There is no way of obtaining the result of the executed runnable, if necessary. You will have to use a callable for that, explained in the following sections. Submit runnable. The Java Executor Service submit runnable method also takes a runnable implementation, but returns a future object. This future object can be used to check if the runnable has finished executing. See an example. The submit method returns a Java future object which can be used to check when the runnable has completed. Executor Service 3. Submit callable. The Java Executor Service submit callable method is similar to the submit runnable method except it takes a Java callable instead of a runnable. The precise difference between a callable and a runnable is explained a bit later. The callable's result can be obtained via the Java future object returned by the submit callable method. Here is an executor service callable example. See an example. The above code example will output this. Asynchronous callable. Future. Get equals callable result. Invoke any. The invoke any method takes a collection of callable objects, or sub-interfaces of callable. Invoking this method does not return a future, but returns the result of one of the callable objects. You have no guarantee about which of the callables results you get. just one of the ones that finish. If one of the tasks complete, or throws an exception, the rest of the callables are cancelled. See an example. This code example will print out the object returned by one of the callables in the given collection. I have tried running it a few times, and the result changes. Sometimes it is task 1, sometimes task 2, etc. Invoke all. The invokeAll method invokes all of the callable objects you pass to it in the collection passed as parameter. The invokeAll returns a list of future objects via which you can obtain the results of the executions of each callable. Keep in mind that a task might finish due to an exception, so it may not have succeeded. There is no way on or future to tell the difference. See an example. Executor Service 4. Executor Service Shutdown. When you are done using the Java Executor Service, you should shut it down, so the threads do not keep running. If your application is started via a main method and your main thread exits your application, the application will keep running if you have an active Executor service in your application. The active threads inside this Executor service prevents the JVM from shutting down. Shutdown. To terminate the threads inside the Executor service, you call its shutdown method. The Executor service will not shut down immediately, but it will no longer accept new tasks, and once all threads have finished current tasks, the Executor service shuts down. All tasks submitted to the Executor service before shutdown is called are executed. Here is an example of performing a Java Executor service shutdown. Executor service shutdown. Executor service shut down now. If you want to shut down the Executor service immediately, you can call the shutdown now method. This will attempt to stop all executing tasks right away, and skips all submitted but non-processed tasks. There are no guarantees given about the executing tasks. Perhaps they stop, perhaps they execute until the end. It is a best effort attempt. Here is an example of calling Executor service shutdown now. Executor service shutdown now. Executor service await termination. The Executor service await termination method will block the thread calling it until either the Executor service has shut down completely, or until a given timeout occurs. The await termination method is typically called after calling shutdown or shutdown now. Here is an example of calling Executor service await termination. Executor service shutdown. Executor service await termination. Executor service v25. What is thread pool? The Java util concurrent thread pool executor is an implementation of the Executor service interface. The thread pool executor executes the given task, callable or runnable, using one of its internally pooled threads. The thread pool contained inside the thread pool executor can contain a varying amount of threads. The number of threads in the pool is determined by these variables: core pool size, maximum pool size. If less than core pool size threads are created in the thread pool when a task is delegated to the thread pool, then a new thread is created, even if idle threads exist in the pool. If the internal queue of tasks is full, and core pool size threads or more are running, but less than maximum pool size threads are running, then a new thread is created to execute the task. Creating a thread pool executor. The thread pool executor has several constructors available. For instance, see an example. However, unless you need to specify all these parameters explicitly for your thread pool executor, it is often easier to use one of the factory methods in the Java util concurrent executors class, as shown in the Executor service text. Thread pool I. We can create following 5 types of thread pool executors with pre-built methods in Java util concurrent Executor's interface. Fixed thread pool executor creates a thread pool that reuses a fixed number of threads to execute any number of tasks. If additional tasks are submitted when all threads are active, they will wait in the queue until a thread is available. It is best fit for most of the real-life use cases. Thread pool executor equals thread pool executor, executors. New fixed thread pool 10. Cached thread pool executor creates a thread pool that creates new threads as needed, but will reuse previously constructed threads when they are available. Do not use this thread pool if tasks are long-running. It can bring down the system if number of threads goes beyond what system can handle. Thread pool executor equals thread pool executor, executors. New cached thread pool. Scheduled thread pool executor creates a thread pool that can schedule commands to run after a given delay, or to execute periodically. Thread pool executor equals thread pool executor, executors. New scheduled thread pool 10. Single thread pool executor creates single thread to execute all tasks. Use it when you have only one task to execute. Thread pool executor equals thread pool executor, executors. New single thread executor. Work stealing thread pool executor creates a thread pool that maintains enough threads to support the given parallelism level. Here parallelism level means the maximum number of threads which will be used to execute a given task at single point of time in multiprocessor machines. Thread pool executor equals thread pool executor, executors. New work stealing pool 4. Thread pool 2. 26. What is fork join pool in Java? Basically, the fork join breaks the task at hand into mini tasks until the mini task is simple enough that it can be solved without further breakups. It's like a divide and conquer algorithm. One important concept to note in this framework is that ideally no worker thread is idle. They implement a work stealing algorithm in that idle workers steal the work from those workers who are busy. See an example. Fork join pool. The fork join pool is basically a specialized implementation of executor service implementing the work stealing algorithm we talked about above. We create an instance of fork join pool by providing the target parallelism level i.e. the number of processors as shown below. If you use a no-argument constructor, by default, it creates a pool of size that equals the number of available processors obtained using above technique. Although you specify any initial pool size, the pool adjusts its size dynamically in an attempt to maintain enough active threads at any given point in time. Another important difference compared to other executor services is that this pool need not be explicitly shut down upon program exit because all its threads are in daemon mode. There are 3 different ways of submitting a task to the fork join pool. 1. Execute method / desired asynchronous execution. Call its fork method to split the work between multiple threads. 2. Invoke method / await to obtain the result. Call the invoke method on the pool. 3. Submit method / returns a future object that you can use for checking status and obtaining the result on its completion. Fork join task. This is an abstract class for creating tasks that run within a fork join pool. The recursive action and recursive task are the only 2 direct, known subclasses of fork join task. The only difference between these 2 classes is that the recursive action does not return a value while recursive task does have a return value and returns an object of specified type. In both cases, you would need to implement the compute method in your subclass that performs the main computation desired by the task. The fork join task class provides several methods for checking the execution status of a task. The isDone method returns true if a task completes in any way. The isCompleted normally method returns true if a task completes without cancellation or encountering an exception, and isCancelled returns true if the task was cancelled. Lastly, isCompleted abnormally returns true if the task was either cancelled or encountered an exception. Core classes used in fork join framework. The core classes supporting the fork join mechanism are fork join pool and fork join task. Fork join pool I. Example implementations of fork join pool framework. In this example, you will learn how to use the asynchronous methods provided by the fork join pool and fork join task classes for the management of tasks. You are going to implement a program that will search for files with a determined extension inside a folder and its subfolders. The fork join task class you are going to implement will process the content of a folder. For each subfolder inside that folder, it will send a new task to the fork join pool class in an asynchronous way. For each file inside that folder, the task will check the extension of the file and add it to the result list if it proceeds. The solution to above problem is implemented in folder processor class, which is given below. Implementation source code. See an example. How it works. In the folder processor class, each task processes the content of a folder. As you know, this content has the following two kinds of elements: files, other folders. If the task finds a folder, it creates another task object to process that folder and sends it to the pool using the fork method. This method sends the task to the pool that will execute it if it has a free worker thread, or it can create a new one. The method returns immediately, so the task can continue processing the content of the folder. For every file, a task compares its extension with the one it's looking for and, if they are equal, adds the name of the file to the list of results. Once the task has processed all the content of the assigned folder, it waits for the finalization of all the tasks it sent to the pool using the join method. This method called in a task waits for the finalization of its execution and returns the value returned by the compute method. The task groups the results of all the tasks it sent with its own results and returns that list as a return value of the compute method. Difference between fork join framework and executor service. The main difference between the fork join and the executor frameworks is the work stealing algorithm. Unlike the executor framework, when a task is waiting for the finalization of the subtasks it has created using the join operation, the thread that is executing that task, called worker thread, looks for other tasks that have not been executed yet and begins its execution. By this way, the threads take full advantage of their running time, thereby improving the performance of the application. Existing implementations in JDK. There are some generally useful features in Java SE which are already implemented using the fork join framework. 1. One such implementation, introduced in Java SE 8, is used by the Java util arrays class for its parallel sort methods. These methods are similar to sort, but leverage concurrency via the fork join framework. Parallel sorting of large arrays is faster than sequential sorting when run on multiprocessor systems. 2. Parallelism used in stream. Parallel. Read more about this parallel stream operation in Java 8. Please subscribe our channel. We will come soon with many more interview questions. Please like video and leave your comment.